Now, this was it for the sample study. So for a sample study, you don't have much choice. You take a sample, then you take a mean, and you take a standard deviation. Then you wean for the mean, and you wean for the standard deviation. And as we saw, the sample mean is a good value for inferring the population mean, and the sample standard deviation, if you adapt it a little bit, it's also a good estimate of the population standard deviation. But that's it. You don't have much more to do than that because it's just one sample. But now we go to the next one, let's say, in terms of how this complexity is increasing. And the next one is the observational study, right? Where in the observational study is the one that we take 2 samples and compare them. So again, the overview of the pipeline, we've discussed this before, so I'm going to go very quick. And basically, it's an observational study. You come up with an idea, again, about a population of interest in the same way that you did before, but in this case, your idea is related to the possible relationship between 2 factors. So you're saying basically that if you measure something in one group and you measure something in another group, one of them will be, let's say, larger than the other. Right? If you, I don't know, let's say, again, if we go for the same example we saw before, I could say, you know, the salary of a teacher in Denmark is larger than the salary of a teacher in Sweden. Although that would be hard to compare because of different money, different types of crowns, but let's just say something like that in general. And that's your hypothesis. Your hypothesis is that this one is larger than that one, and that involves 2 different groups that you measure. Right? It's a bit different than the one sample study when you just think of a hypothesis of one value of one. Then you do the same thing. You go there and you sample your population of interest. And in this case, of course, you have 2 actually groups that you want to sample, or sometimes you have also just one population to sample. But usually, in this case of observational study, let's just say that you have 2 populations of interest and sampling both, even though they may conceptually be the same. But let's not worry about that. So you have 2 groups now, okay? 2 samples. Now you measure the samples you obtained regarding your idea hypothesis. You measure only the 2 factors that you are interested in, right? So don't measure more than that because, again, you need to be objective and concrete. So since you're trying to check for the difference between 2 things, you measure only what you want to have. Then you analyze the relationship between these 2 measured factors. You can use, for example, correlation or linear regression. And of course, hypothesis testing, which is what you finally will do. It's just this comparison of one thing against the other. And then you infer the population, the value of the population from the sample. In this case, you infer the value of the, let's say, difference between these 2 things, or the relationship between these 2 things in general. That is what you're trying to infer. And your population is the same. There is this thing that is your population is out of reach. You don't know it. You measure the sample. From the sample, try to infer what's happening with the actual population. Exactly the same as before. Only have 2 samples. Now, in this case, you have 2 variables. We call them variables sometimes when we are talking about 2 sets of measurements, let's say. So you are analyzing 2 variables at the same time. You start by applying the same things that you learned for one sample, but you apply to each one of these variables at the same time. So each one of these different sets of measurements that you took at the same time, right? Why you do this? Why would you start by applying this for one sample? Because when you analyze 2 things at the same time, there are complexities that come from this, and you from the analysis of these 2 things at the same time, you don't necessarily understand that the variables independently. So it might be hard to understand that a certain effect is not based on the comparison of the 2 variables, but it's actually based on some individual characteristics of each one. So it makes more sense to start from an exploratory analysis where you start by describing and visualizing each of your variables, in the same way that we did before with one sample. So consider them as like two different ones. Then again, you show the summary statistics of each variable independently. So you kind of like profile these two variables independently so that you have a good idea of how they work separately from each other. And then later you will be able to differentiate better between patterns that are individual to each variable and patterns that are actually based on the correlation between the two. And not only that, but also later that will help you decide which of the hypotheses that you're going to run and so on. So it's very important, even if you have two variables, to understand them individually before you understand how they work together. That helps a lot. And that's something you should do in your presentation when you finish your data. This is an example of how to visualize two variables at the same time. So when you have just one variable, just one data set, you would use a histogram, right? That would be the most common one. But for two variables, it's a bit hard to have these two histograms at the same time because they kind of would overlap each other. It would be a little bit hard to compare. So the scatter plot is by far the most common type of visualization for when you have two variables at the same time. So basically, what do you do? Well, you put each of your variables of your data set, one on the x-axis, one on the y-axis, and then you put a point in where this two on one element where it meets, let's say, these two variables at the same time. So let's say one. Let's use this as an example, a quick example, so you understand what I mean. There were two variables here that were measured together, right? So the waiting time between eruptions and the eruption duration. Sorry, this data set, again, I went a little bit too far. This data set is measurements of eruptions of a geyser called Old Faithful in the Yellowstone National Park in the United States. Okay, so they measured, every time this geyser erupted, they measured the waiting time between eruptions. So how much time it took between the previous eruption and the current eruption, let's say, and how much this eruption, what was the duration, how long it was, this water that goes up. A geyser is this kind of like volcano of hot water that goes up from the ground. So they measure these two things at the same time. So that's why they have these two variables, which actually by themselves comprise two different data sets, right? But they were measured together. So each variable is mapped to one axis. We have the eruption duration here in the x-axis and the waiting time between the eruptions in the y-axis, like this. And then you just plot a point, right? So first eruption, well, it took, I don't know, 52 seconds of waiting time, and the eruption lasted 1.6 minutes, right? So they just kept measuring and measuring and measuring. Each point is one measurement that has, well, each point is, let's say, one sample that was measured two different ways, the waiting time and the duration. And then patterns may arise when you plot this in a scatter plot like this, because then you can see that, for example, that's very interesting that in this case here, you can kind of like differentiate these eruptions into two different sites, two different types, sorry. There are some eruptions here who they're very quick, and these are usually the ones that happen faster between one eruption and the other. So let's say there's a pattern that if it doesn't take too long between one eruption and the other, then the eruption will be short. Kind of makes sense, right? Because let's say the water didn't accumulate as much or something like this. But what we don't know, we can't really assume. It's just that what we can see here is that whenever the waiting time between the eruptions is very small, then the duration of the eruption is also quite small. And the opposite's the same. When it takes too long between eruptions, so for example, when it takes around 80 to 90 minutes between one eruption and the other, then usually the eruption takes longer. So it takes up to like 4.5 or 5 minutes. So it's very very long eruption, because it took, you can kind of assume, like predict that, because if it takes too long between two eruptions, you can kind of predict that the eruption will be large or last long. Right? And this is by far the most common way that you plot two variables at the same time, and usually it's interesting patterns. And then there's also this line over here, which is the line that we say it's a linear, kind of probably not linear, it's just a trend line, let's say. It's kind of a trend line here that kind of helps you, in a way, predict one variable from the other on average. So, for example, if I say, well, I just saw an eruption that lasted 4 minutes. So I'm wondering how much did it take between this eruption and the previous one? I don't know, because it didn't measure. I just got there 2 minutes before that, and I saw it, and it took 4 minutes. So then I'm just wondering, how long was the previous prediction eruption before this one? Well, if you project this to the line over here, you would say this is probably around 78 minutes or something like this. You can kind of expect that it was 1 hour and 18 minutes since the previous eruption, more or less. Because this is kind of like a trend line here where you see the average between the two variables. And so again, it's just an average trend. So it's not super complicated machine learning. It's just a rough, let's say, prediction. Now, again, in the same way that we saw with the histogram, a visualization is nice and cool and lets you, come up with lots of different hypotheses and ideas. But in order to actually answer a research question, you cannot use, well, mostly you cannot use it. You have to actually have something that, says, yeah, the correlation between these two variables is this or that, right? So you cannot just say, oh, look at the visualization and let's see. No. You actually have to come up with one value, right? And in this case, this value is the so-called correlation coefficient, right? Which is a measure of the strength of the linear relationship between two quantitative variables. It's like a numerical summary of this trend or this behavior that we saw that is going up. When something goes up like this, basically means that these two variables are positively correlated. When one goes up, the other also goes up. So you can expect that if one is large, the other is also probably large, because they're positively correlated. And the correlation coefficient is a measure of the strength of this relationship. So it's a number that says they are 80% positively correlated. Then you can expect that they are actually very strongly correlated. It's usually known as R, or Pearson's R. It's in this form, population correlation. You use Greek letter rho because it's usually like this. When you have population values, you use letters. When you have sample values, you use actual, which is letters. It's English or Latin or something. I don't know. Don't quote. I have no idea what I'm talking about. But the population is usually Greek letters. And this is from I won't go into details here, but this is basically almost the same formula as a variant, but using two different values, variables at the same time, more or less. I won't go into details. It doesn't matter too much. Again, we'll always have this on spreadsheets or for statistical software package. Some notes about the correlation coefficients. First of all, I think can take values between -1 and +1. So basically, it can be negatively correlated and it can also be positively correlated. A negatively correlated coefficient that approaches -1 basically means that the values are correlated but negative. So when one goes up, the other goes down. And in that case, when you look at one value that is, let's say, if it's high, then you can kind of predict that the other one will be very low. That's what it means to be negatively correlated. The sign of the correlation provides the direction of the relationship. A correlation of 0 means that there is no linear relationship. If the correlation is 0 or close to 0, even up to, let's say, 10 or 20%, then you can kind of expect that there's no real relationship. It's purely random. So you cannot predict anything about one variable by looking at the other variable. They're not correlated. They're just randomly distributed when they're together. So it's like two things that have absolutely nothing in common with each other, or very, 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 very little, up to a point where it doesn't really allow you to make a conclusion. There are no units attached to R, so you don't say the correlation is 1.5 some, and then I get like meters or kilos or something like this. There is no unit. It's just a number. It's 0.5. That's very simple. As the magnitude of R approaches 1, the stronger the relationship. By magnitude here, I mean that it's the absolute value. So it doesn't matter if it's negative or positive. As soon as the magnitude is reaching 1, so either close to -1 or close to 1, then the stronger is the relationship. Even if it's negative, you can have a strong negative relationship as long as one thing goes up consistently when the other one goes down. And again, as it approaches 0, the relationship gets weaker up to a point where you can't really make any conclusions about it. And it doesn't matter here if it's X or Y. Like in this formula here, if you change X and Y here, it doesn't matter at all. It's completely symmetric. So again, it's the same as if we change this scatter plot here. I mean, if we change waiting time here and eruption region here, it will still be positive. Although the shape will change just a little bit, but it will still be positive. So it doesn't matter if you change the variables among themselves. And these are some examples of what it means to have some specific value of whole. For example, I like to compare two values. For example, in this case, -1 and some value -1, 0. You might, when you look at this curve like this, and you compare it to this curve like this, you might think these ones are actually more strongly correlated, or have a stronger correlation than this one, because the angle of the line is down very steeply. But the truth is that it's not really related to that. The correlation is stronger if they go down or they go up together more constantly, or in a more consistent way. And in this case, they are more consistently going down together than in this case, even though the angle doesn't matter. This is how it would look if, let's say, if you had something that has 0 correlation. Basically, you cannot feed a line here, no matter how much, no matter where you put a line over here, like this green line here. These green lines, they kind of represent the data in a way, even though there is error, of course, but they kind of represent the in a way. But this here, no matter where you put a line, you will never get a good line. Like you will never get a good line that says, yeah, this kind of represents the data set in a good way. Never. You cannot find that line. That's why the whole region is 0. So basically saying, look, it's completely random. The relationship, these two variables is random or non-existent. So again, just remember that the angle here doesn't matter as long as it's more consistent. So as long as the points are closer to the line, then the relationship is stronger. And now I got to talk to you about something related to correlation versus causality, which is this very important notion in statistics that you have to differentiate correlation and causality. Correlation does not imply causality. What does that mean? just because you find correlation to measure this, like you measured something and you measured another thing, you measure the correlation, you make a scatter plot, they are super strongly correlated. You cannot let yourself go down the path that you made happens, that you start telling yourself that one of these variables is actually causing the other to be like that. It may and it may not. From the correlation itself, you cannot make that assumption. And the reason is that, as far as you know, there could be another unknown element, C. Let's say you have variable A and you have variable B, and then you determine that their correlation is actually very strong. First of all, you don't know if A is causing B or if B is causing A, because the order between them is interchangeable, right? If you change them in the correlation is the same. So you don't know if one causes the other. And actually, as far as you know, there could be another variable C that's external from your observation that you didn't even know that it existed, or you didn't care about the measuring it. And that variable is affecting both A and B at the same time. And that's why A and B are correlated, because they're being affected by something else in the same way. So again, you can never establish causality simply by looking at the correlation. The only well-accepted way to establish causality is to run a controlled experiment. So you have to have the data gathering under control all the way from the beginning. You cannot do an observational study and just measure something from the world and then establish a causality relationship with these two things. You cannot do that. The only well-accepted way is to run a controlled experiment, which is much more complicated than just observing some variables for the. And we're going to talk about this next couple of slides, next few set of slides after this one. This is a nice little example of correlation does not mean causality. These are prices of beer and chicken in Oktoberfest from 1985 to 2018. So someone went to Oktoberfest many times and measured, well, probably not, they just took this from somewhere, and measured like the average price of a beer and the average price of a piece of chicken in Oktoberfest. And then, of course, it goes up, right? So beer goes up, chicken goes up. Well, they both go up, and they kind of go up together. So would you assume that because, so first the beer price goes up, and because the beer price goes up, the chicken also goes up, so one is causing the other? Or would you assume that because the chicken price went up for some reason, then the beer also goes up because it follows? You shouldn't assume that. Actually, the easiest explanation here is that they both go up simply by the way that the market works, or the financial world works. I mean, things get expensive as time goes on. That's how it works. I'm not an economist, so I cannot argue about anything related to that. But the fact is that things simply become more expensive because the money it's worth less, or inflation or something. I don't know. I can't explain. But what I know is that the easiest explanation here is that they seem to go up because other things also up. So there's an external thing that is affecting both beer and chicken at the same time, and you cannot assume that they are both affecting each other. And also you cannot just completely assume that they're not, because you don't know. I mean, maybe the beer price went up and chicken followed it. Who knows? I don't know. The point is that you cannot assume anything. And I have here another example of this correlation implies causation, which is that someone published this. This is from Karakadi also. Someone published this article in 2008 in this website where it says, eating breakfast may beat teen obesity. So basically what they're saying is, if you eat breakfast, then, look, it's a very interesting causality situation. If you eat breakfast, then you may beat obesity. And then they go on to say that researchers analyzed the dietary and weight patterns of a group of 2,000 200 adolescents over a 5-year period. And then they realized that those students who ate breakfast regularly had a lower percentage of total calories. So you eat more breakfast, you have lower percentage of total calories from saturated fat, and eat more fiber and carbohydrates than those who skip breakfast. So if you skip breakfast, then you have more percentage of total calories from saturated fat. It's fine. Also, regular breakfast teachers seem more physically active than breakfast skippers. Now, look, sorry, I'm not saying that there is no relationship between them. There probably is, right? They measured it. They could see the correlation between eating breakfast and having less saturated fat or eating more fibers. There is a correlation. The problem here is that they are trying to establish a causality between these two things. They're trying to say that because you ate breakfast, you will have less calories. And you cannot assume that. For all we know, there is some other factor here, external, that is affecting these kids, and so they have breakfast and they are more physically active. Maybe these guys are playing sports. Maybe they're doing sports in the morning, so they eat breakfast before they go to sports training, and they're more physically active. So that's why they like to eat breakfast, or they feel like it's very important to eat breakfast because, or else they will be tired and they won't be able to, or they won't have the energy to practice their sports. While if you're some of those who are not having sports training, they kind of skip breakfast because they don't care too much, or maybe because, I don't know, they ate during the night. Maybe those guys who skip breakfast, they were eating at night, so they didn't feel like eating breakfast. Eating during the night maybe is something that also makes you have more calories from saturated fat and to be less physically active. I don't know. What matters is that for all we know, we cannot assume that one thing is actually causing the other. Actually, the relationship could be the opposite, right? Maybe because they're physically active, like I said, I guess the same. Because they're physically active, they are eating more breakfast, even though it's not about force training. So the relationship of the direction of the relationship between one to another, that is the one thing that you cannot assume. All you can assume is that they are correlated. Correlation exists because we measured it, and that's it. And then you can make assumptions like, well, it feels like maybe it is or maybe it's that, but you can never really determine the causality from the correlation. That's very, very important. Finally, you may be thinking, well, if I do this measurement of this difference between these two data sets, right? I have two data sets. One has its own specific standard deviation. The other one has some other specific standard deviation. How do I determine the standard deviation of the entire thing? Like if I measure the difference between them, like okay, the difference between the salaries of what we said in the beginning, the salaries between a person in a lecture in Sweden and a lecture in Denmark, then let's say I compute this difference and I realize that in Denmark lectures Sweden. Again, we can go back to that question we had before about how certain am I of that? How representative is this final value that I just measured, right? Well, then you would have to compute the standard deviation the same way that you compute the standard deviation. In the other case, you have the standard deviation of the actual value that you just computed. And I just wanted to leave this here. You don't really have to know this. I just wanted to leave this formula here to show you that it's quite interesting that when you take one minus the other here, like you're determining difference between two means, right? Like the mean salary in Denmark and the mean salary in Sweden, and then you subtracted them in order to determine difference, whether one is larger than the other. Standard deviation is actually the sum of the standard deviations. This is the formula here that you can use. but it's interesting that it's actually sum and not subtraction, because even though you're subtracting two values, the both data sets still vary a lot, and the variation of their combination it's still growing and not diminishing just because you are subtracting. Right? When you mix two data sets into one thing, like what we're doing here by taking one minus the other, then the standard deviation or the variance of the set it goes up because there are more values, there are more possibilities of variance or of variation or variability. They have double the data points, and these data points are kind of like interacting with each other. So the variance actually goes up. And that is very interesting and very important to keep in mind, because later, those of you who chose to do two sample studies in your data gathering will have to actually compute the variance of the difference. And this is the formula right here. So if you're going to do sample study and later you don't know what to do, come back to me, ask questions, and I will kind of give you a little bit more indication of what you should do.